Let's be honest, for a lot of us, the word calculus conjures up these images of dusty, intimidating textbooks, right? Just pages of symbols that don't make any sense. But what if I told you that behind all that complexity, there's an idea that's actually stunningly simple and incredibly powerful? Well, today we're going to pull back that curtain and see how calculus gives us a whole new language to understand our world in motion.
It all kicks off with one fundamental problem. Just think about it for a second. Our world never, ever stands still. A car is accelerating, a population is growing, planets are zipping around the sun. So how on earth do you take a precise mathematical snapshot of a world that's defined by constant change?
Okay, so take a look at this. It might seem like just a chaotic jumble, like a radio wave or something, but it's the perfect way to visualize the challenge. This is a dynamic system, and before calculus came along, we just didn't have the words, the mathematical language to talk about this kind of complex, continuous movement. Calculus gave us those words. So let's dive into the first of two really big ideas here. The first half of calculus, it's called differential calculus, is all about answering one simple question. How fast is something changing right now, at this exact instant?
And here is the key insight, the secret sauce, really. Calculus thinks about functions in pairs. So you have one function that tells you where something is, your position on a road. But then there's a second function, the one calculus helps us find, that tells you how fast you're going at that very moment. It's all about that relationship between a quantity and its rate of change.
This table really makes that pairing concrete. So on the left, we've got our position functions. For a straight line like y equals 2x, the growth rate is always just 2. Simple, right? But now look at the curve, y equals x squared. Its growth rate is 2x, which means the slope itself is constantly changing. Every function has its own unique slope function, and figuring that out is the first major trick of calculus. And that slope function, well, it has a proper name. It's called the derivative. It's the slope at one single infinitesimally tiny point on a curve. And honestly, the best way to think about it is your car. Your odometer, that tells you the total distance you've gone. That's function 1. The derivative, that's your speedometer, telling you your exact speed right this second. That's function 2. Okay, so that's half the story. But what if we flip the script? What if we already have all the speedometer readings, a complete record of every instantaneous change? Can we use all those little pieces to figure out the total distance we traveled? Well, this is the second half of calculus, integration. To really get this, let's play with a simple little puzzle. So in that first column, the one labeled F, we've just got a sequence of numbers. The second column, labeled V, well, that just shows the small changes, or the differences between each number. So from 0 to 2, the change is 2. From 2 to 6, the change is 4. You get the idea. All right, now for the fun part. What happens if we just add up all those small changes in the V column? So we have 2 plus 4 plus 1 minus 3 plus 5, and we get 9. So the number is 9. The big question is, where did it actually come from? I mean, really. Take a look back at that first column of numbers. See any connection? And there it is, the aha moment, the sum of all those tiny individual changes. It's just the total change from the very beginning to the very end. The last number, 9, minus the first number, 0. This little puzzle reveals this incredible, deep truth. Finding slopes and summing up changes are two sides of the same coin. They undo each other. And that idea right there is the heart of what's called the fundamental theorem of calculus. So we have these two incredibly powerful tools. One for finding the rate of change in a single instant, and another for rebuilding the whole story from all those tiny changes. And with just those two ideas, we can suddenly describe and predict, well, an absolutely incredible range of things. So where does this stuff actually show up in the real world? Well, for starters, calculus is an optimization machine. By finding the exact point where the rate of change is 0, the very bottom of a curve like this, it can calculate the absolute fastest route for your trip. It's also the language of economics. When you hear phrases like marginal cost or elasticity of demand, those are just fancy words for derivatives. Calculus lets economists build models that show how tiny changes in price can ripple through the entire market. And oh man, physics is just built on it. Think about the work it takes to stretch a spring. The force changes as you pull, right? Figuring out the total work done. Yep, that's an integration problem. In fact, it turns out force is actually the derivative of potential energy. It's all connected. And the list just goes on and on and on. We're talking about predicting the exact orbits of planets, modeling the growth of populations, even understanding the beautiful weirdness of chaos theory, or optimizing a financial portfolio. It is literally everywhere. You know, this power was so unique, it was like a signature. There's this great story where a really complex physics problem was sent to all of Europe's top mathematicians. A solution came back, but it was anonymous. But one mathematician, Johann Bernoulli, he knew immediately who sent it. He said, "I recognize the lion by his claws." That kind of powerful, elegant thinking could only have come from one person, Isaac Newton.
So as we wrap up here, it's worth remembering that calculus isn't just a set of tools you use to solve problems. It's bigger than that. It represents a fundamental shift in how we see the world. It's like a whole new language for describing reality itself. And nothing shows off this new language better than this right here, Euler's identity. It's often called the most beautiful equation in all of mathematics. Using the framework of calculus, it weaves together the 5 most important constants in math, 0, 1, e, pi, and I, into one perfect poetic sentence. It's just incredible. And let's not forget, this profound language, it didn't just fall out of the sky. It was built. It's a deeply human thing, you know? It was created piece by piece through curiosity and arguments and people working together. It's really a testament to our deep drive to find a way to talk about the world's beautiful complexity. Ultimately, calculus gave us the words and the grammar for a world in motion. It allows us to write the story of change itself, from the tiniest particle to the largest galaxy. So the only real question left is, what stories are we going to choose to tell with it next?